You perform a reaction, a chemical reaction in the lab. In order for you to perform this reaction, you cannot just go open the chemical containers and simply say, okay, here's a handful of this, a handful of that. That simply does not happen. And experiments are not run like this. What you have to do here is you have to calculate how much of these reactants or these chemicals that you are going to use in the reaction in order to determine how much of the products will be obtained or will be produced. So just like when you go on a trip, you have to make sure you have enough gas in the car, you have water on the roadways, etc. So the same thing here is we have to account for the amount of our reactants. So what does this word stoichiometry mean? Stoichiometry is the numerical relationship between chemical amounts in a balanced chemical equation. So that's the numerical relationship. What it does is that it helps us predict the amount of products that will form in a chemical reaction based on how much reactants you use. So, and then determine how much of the reactants you need to form a given amount of product. So when you, for example, an example is building materials. You cannot just go buy 5 tons of wood and timber, right, for a project that requires building a table and its chairs. That makes no sense. The same thing here in chemistry is we have to know how much we're starting with and know how much of the material will be formed, the product will be formed. So here's a reaction. We have to always think this way, is that whenever we look at a chemical equation, we have to be able to interpret it in multiple ways. The most important one is the one in the middle. It's the one with moles. And of course, the one with the mass is, again, that can be applied to it. But let's actually write the molecular, molar, and mass interpretations for the following reaction. If you have not done this, I would highly recommend that you pause and do that. So you should pause now and do it, and then replay in order to check your answer. But let's start. So then the molecular interpretation would be you have one molecule of C3H8, which is propane. Just going to write one molecule of this. This one would be 5 molecules, 3 molecules, and for water, it is 4 molecules. So again, this is the molecular interpretation. For the molar interpretation, it would be now simply in moles rather than molecules. So you would say 1 mole, 5 moles, 3 moles, and 4 moles. So that's, again, the molar interpretation. And then finally, the mass interpretation is, remember what we have been talking about, is that this is moles and it has a mass. And then within that mass, you have 6.02 times 10 to the 23rd of that compound, atom or ion or molecule. So in this case, that would be multiplied by its molar mass. So you have 1 mole of this. You would have to find the molar mass of that, which would be, in this case, so this would be 44.11 grams This would be 5 times 32 grams. Again, I'm getting those numbers from the periodic table. This would be 3 times 44.01 grams, and this would be 4 times 18.02 grams. Okay, so that's the mass interpretation. So again, if you should be really, really quick at calculating the molar mass, because we don't want to spend too much time on that. So the molar mass, again, comes from here. So I had in C3H8, I had 3 carbons, multiplied them by 12.01, and I had 8 hydrogens, multiplied 8 by 1.01, and that adds up to C3H8, which is 44.11 grams. Now, it is really essential that you understand the conceptual framework of this. So again, 1 mole has this mass, and within this mass you have 6.02 times 10 to the 23rd. Now, this is the equation, but then we need to be able to use this in the lab. Not always you start with 1 mole of C3H8. This may be too much. Or 5 times 32. That's a huge amount. You usually in the laboratory, you work with smaller amounts. Let's say, 5 grams, 10 grams, or even 0.5 grams. So I don't want to belabor this, but that's the idea behind it. So take a minute and make sure you understand this, because it's really, really important. So now let's look at the molar ratio, or the mole ratio. Now I'm going to do, as we did here, 1, 5, 3, 4. I'm also going to write these numbers on the top. 1 to 5 to 3 to 4. So these are the ratios. So we need to be able to get the mole ratio readily from now on, and it's easy to find. This is like a recipe. If you have to use 5 eggs and 2 cups of flour to make 1 cake, well, that's the ratio of what? 5 eggs to 1 cake. So 5 eggs is needed to make 1 cake. 2 cups of flour would make 1 cake. And the ratio of eggs to cups of flour would be 5 to 2. That's the idea here. It's really, really the same. So whenever they say to you, chemistry is related to baking and cooking and all that stuff, it is true. All of these are really chemistry processes, in a sense, chemical processes. So let's actually look at the mole ratio. So if I need the mole ratio, let's say, of C3H8 to CO2, all I need to do is read these numbers. So if I have C3H8 to CO2, that ratio would be 1 to 3. If I need the ratio of O2 to CO2, once again, that would be, let me use a different color here, that would be 5 for oxygen, and of course the 3 for the carbon dioxide. So that would be 5 moles to 3 moles, so on and so forth. It is important that we're able to get this number, and again, you get it from these numbers on the top, and again, they are written over here as well. You also have some information here. So let's look at the stoichiometry operations. Now these begin from simple ones like 1 conversion factor all the way to 3 conversion factors. Now, of course, if you incorporate dimensional analysis, that would be even more, as you are aware of that. So just know one thing always, a rule of thumb, is that in stoichiometry, you always use the mole ratio. Like, it has to be one of your factors. If it is the only factor, then that is the only factor. So you always use a mole ratio. It's like a recipe. You cannot go from one substance to the other numerically without, again, using that ratio. Very well. So here the question says, how many moles of C3H8 are required to produce 1.65 moles of CO2? Now, again, I'm working with this equation. This is all in relation to this equation. So I might have to copy this actually into the next page. But let's actually look at this. It says, how many moles of C3H8? That's my unknown. I need the moles of C3H8 if are required to produce 1.65 moles of CO2. So I'm going to start with that right away. 1.65 moles of CO2. And I need to end with the moles of C3H8. Very well. That's what the question is asking. So right away, I'm concerned with CO2 and C3H8. CO2 and C3H8. So let's erase these circles so we can do that one more time. So the ratio of CO2 to C3H8 is 3:1, meaning you need 1 moles of C3H8 to produce 3 moles of CO2, right here, right here. So I'm going to write this down on the side here so you can see it. 3 moles of CO2 to 1 mole of C3H8. So that is your only conversion factor, and therefore going to have to plug this into here. So if I have, how do I know? Then you ask, what goes in the denominator? Dimensional analysis once again. Moles goes on the bottom. So you have 3 moles of CO2. And of course, they cancel out. And what goes on in the numerator is the mole of C3H8. So that's 1 mole of C3H8. So we're dividing here. Dividing 1.65 by 3. Now, sig figs, we have 3 sig figs, so must end with 3 sig figs. So 1.65 divided by 3 would give us 0.550 moles. That is our answer. Now, in the next 2 problems, in another video, in the next 2 videos or 1 video, I want you to think about what information would be required, because again, these are relevant, but of course they involve now more steps. So this one, I'm going to tell you from now, involves 1 more step, and this one involves 2 more steps. So think about them before we get to the next video. All the information that you need is right here. And then in the video, we will go over them.